Okay, good morning, everyone. Welcome to the conference on New Thinking in Industrial Innovation and Technology Policy, Perspectives from Developed and Developing Countries. I'm Eric Verhoeven. I'm a professor here at Columbia in the Economics Department and in SEPA. The co-organizers of the conference are here in the front row, happily populating the front row. Josh Whitford, Laura Boudreau, and Andrew Schrank somewhere just walked out the door. It's great to see everyone here. This conference is being sponsored by the Columbia Center for Political Economy, which Suresh is going to come up and say a couple of words about, by the Center for Development Economics and Policy, which I co-direct with Kiki Papelkis, who's also here, and also SEPA has a new initiative on technology and innovation, which is also co-sponsor. Before I forget, I want to make sure that we thank the person who's been doing the heavy lifting on the organizing, who is Alina Jennings, who's sitting out there on the table. Maybe give her a round of applause so she can hear. It's no mean feat to organize a conference like this one, and so she should get a lot of credit for that. Also, Anna Marchese, Catherine Burke, and Madeline, I hope I'm pronouncing that right, Madeline Naley from the Center for Political Economy have also been very helpful. So let me say a couple words briefly about the conference itself. The motivation is that after many years in the wilderness, industrial policy is back. I think that's not a surprise. Everyone realizes that. It's back on the front burner of policymakers. It's also sort of newly in intellectual conversations in various fields. But in part because of those wilderness years, our sense is that the knowledge base to guide industrial policy and to do smart industrial policy is still pretty thin. And so that's really the motivation for this conference, is to start building a community of people who are involved in strengthening that knowledge base to guide policy. I think, I can speak for myself. I think I can speak for the co-organizers that it's encouraging that there's this openness to industrial policy interventions, but we need to be smart about it and we need to be evidence-based about it. And so that's part of the idea here. Partly we're going to hear some good papers. We're excited about the program. It's great to have all of you here, and it's partly about building this community of scholars. One thing you may have noticed about the program is we're trying to be interdisciplinary, right? So we're trying to get sociologists and public policy people and political scientists and engineers and economists in the same room together talking to each other. That interdisciplinarity, if that's a word, is part of the mission of the Center for Political Economy, which Suresh is going to talk about. It's also, I think, called for by the topic. To understand how to do smart industrial policy, you really have to, for instance, go out and talk to people, which sociologists are good at, which economists are pretty bad at generally. You have to understand the technology. You have to understand the details of sort of where the technology is going, how to sort of forecast a little bit how these things are going to evolve. For that, you need that's something engineers are good at, that economists and social scientists, are not. And we also need to be in conversation with practitioners to find out what's really happening on the ground and what are the concrete challenges that people are facing. Anyway, so please make an effort today. We're sort of forcing that by putting people on the same sessions. You'll have some mix of disciplines, and please make an effort to sort of reach out and talk to people who are not in your discipline today. This is the first event of. We have a new idea lab within the Center for Political Economy on firms and industrial policy. It's our first big event. We hope that this will continue. Josh and I are co-directing that. So stay tuned and please spread the word and get people coming to Columbia next year. Okay, Suresh.
All right, we'll take 10 seconds just to introduce the Center for Political Economy, which is a new center, relatively new center at Columbia that's co-directed by me, Ira Katz-Nelson, and Katharina Pister. And the idea is that we have one of these Hewlett Foundation kind of 5-year grants to kind of build new thinking in political economy. And so we've sort of hived it off into a set of idea labs that kind of are supposed to be interdisciplinary groupings of scholars. And I think the firms in industrial policy one is a great one with kind of input from both the business school and economics and sociology kind of all coming together. And we sort of have a similar interdisciplinary one around like labor market institutions and work and labor. And we have one on finance and money. And then one will be starting up next year on climate. And so that's kind of like an overview of the lab. And we've been doing, so graduate students in the room, we have a graduate grant program, there's a faculty grants program, then there's lots of programming the center's doing, so keep your eye out for all of these things that are coming along. And if you're not on the mailing list, it's political economy at columbiaworldprojects.columbia.edu or something like that, and you can and you can get on the mailing list. All right, yeah.
Welcome everybody. I'm Andrew Schrank. other than calling 5 and 1 while you're speaking today. This might be the only time you hear me. But it's my distinct pleasure to, that's supposed to be a joke, apparently it didn't. Thank you. You know you're in trouble when you have to call attention to your, anyway, it's my distinct pleasure to introduce our first keynote today, entitled The Microfoundations of Technology Outcomes, Building the Intellectual Foundations, Data and Analytic Tools to Inform Strategic Science and Technology Investment, by Professor Erica Fuchs of Carnegie Mellon University. Erica is Professor of Engineering and Public Policy and the College of Engineering at Carnegie Mellon. She has been the director of the Pilot National Network for Critical Technology Assessment, funded by the National Science Foundation's new Directorate in Technology, Innovation, and Partnerships over the course of the past year or so. She's on President Biden's White House Advisory Committee for Trade Policy and Negotiations. She's on the Board of Trustees for the, I can't read my writing, the National Semiconductor Technology Center at the Department of Commerce. And most important to about half the people in this room, she's a member of the National Bureau of Economic Research. And it's really my pleasure to welcome Erica and to thank her for joining us today.
Great. Well, it is an honor to be here. And I, as Andrew was reading the title of my talk, I said, oh, is that the title of my talk? Oh, dear. In terms of, I probably gave that at some rushed moment, and I was like, I think it works. What I want to talk today about is primarily the initiative I've been leading for the past year, which largely has felt to me that it's more on behalf of government than on behalf of any one university. We've just released, if you go to, I'm feeling really good that we have a short URL, if you go to nncta.org, we have just released our report at the end of the first pilot year on behalf of 13 universities that have been engaged in this first year pilot. That's what I will talk about, but I want to give you a little bit of a history of myself before I start talking, because that's where I would like to end the talk. So as a scholar, I am an engineer. I am a material scientist, and I am largely motivated by frustration. And when I say that I'm largely motivated by frustration, my earliest work came about in terms of thinking about gains from trade. And as an engineer, I was thinking about the models I was building in the engineering lab for companies, which suggested that no matter where you located your manufacturing, it would basically the companies just wanted to know, and it was a large consortium of companies, which technology was most competitive. And I had just lived working at the United Nations in China and been on a number of shop floors in China, and I was like, but the variables, every single variable in my model that's supposed to be looking at which technology is most competitive changes. The yields, the downtimes, at every single process step. And I said, I can't believe it's the same answer. And so I talked to my professor of engineering at the time, and I said, I really want to look at this. And he said, well, do that on your own time. And so I did, but he got me access to the companies who were doing the production overseas in developing East Asia. And sure enough, when you moved manufacturing overseas to developing East Asia, not only did all the input variables change, but the most competitive technology changed as well. And so what that meant is that instead of, as we might think traditionally in gains from trade, that we make the same widget here as we make somewhere else, and therefore we now get in the new location that new widget cheaper and everyone's better off. Instead, you had a different situation where you get a different widget somewhere else. And so depending if there's gains from trade from an innovation perspective and a technology trajectory perspective, or losses from trade, would depend on what that new technology was, and whether we were diversifying our technology portfolio, or, as was the case in the particular technology that I was looking at, it was basically cheaper to do the older technology, which had more labor content overseas. And it wasn't about not wanting to move that technology for IP rights. It just literally was the cheaper way to go. And so I think it's that inside the black box thinking, inside the black box of technology change thinking that we really need in industrial policy. And where I am going to start and end, and that's where I've made, I could give repeated examples throughout my career, that's where I've made my career, and I believe that we do need a field of students who can do that, who are bilingual and who can speak across the disciplines and the technology specialties. And we do that at Carnegie Mellon in a department called the Department of Engineering and Public Policy. We've done that for 30 to 40 years. I have 2 students here who are sitting in the room, and I want to talk about why the whole country needs to do that now. Okay, great. Our report. So, zooming forward in my career, I, in another moment of frustration, had begun during the pandemic to essentially come to believe that we needed, I've written a paper that is called What National Technology Strategy Is and Why the U.S. Needs One. That was before the Chips and Science legislation came out. And I had increasingly come to believe that we needed analytics to inform that national technology strategy, due to work actually with Nikhil, who's sitting here in the room, and Alfonso, that we could, with academic tools and bringing engineering and the social sciences together in integrated interdisciplinary teams, we could indeed be strategic and forward-looking. And there are tools in engineering that do that, and we can talk, I'm going to talk about that. To do that well, we needed to leverage integrated interdisciplinary teams, that we needed to focus the area that I believe economics struggles with, and all of us struggle with. Actually, there's multi-objective optimization in engineering, but I would say all of us struggle with, is firms maximize profit. A country has multiple missions. A country has national security, it has the economy, it has societal well-being. So how do we start to think about, maybe our job is not even the trade-offs between those national missions, or the win-wins, maybe it is. Maybe our job is to put in front of legislators more clearly, so they can then choose their values. What are the trade-offs and the win-wins across the national missions, but even making those directions clearer? What are the implications? Maybe the economists want to go towards, or the engineers towards optimizing across multiple national missions. But I would argue a first step is even making that connection between technological decisions and national missions, and what would the outcomes be? We need, for the government, a neutral third party. And when I say neutral, everyone, whether it's the universities, and I've really lived that this year, industry, different agencies, everyone has a stake. So how do you develop an objective, trusted, and I don't know what objectivity means, frankly, right? How even where you focus the light or the lens changes the what we've looked at versus what we haven't looked at. But how do we start to think about a trusted third party that is outside of stakeholder dynamics, industry or government? And then finally, I came to believe, or I argued, actually I did 3 testimonies. So if the easiest way to find that is actually if you Google Erica Fuchs, Peter Coy, New York Times. And he has an article where he links to all of them. I had testified twice in the House and once then in the Senate just before the Chips and Science legislation, that this needs to operate in a highly flexible, distributed model, capable of rapidly mobilizing and reconfiguring star private sector, government, and academic talent, data, and resources for the country to inform national technology strategy. And the reason I came to that was, frankly, I had studied DARPA, and I had studied the way DARPA orchestrates technology directions and orchestrates and bridges gaps between, really, in creating new fields and communities. And so I believed we needed something like that, but not like that, to really orchestrate the talent across the country, across disciplines, toward helping the government inform national technology strategy. Okay, so as rarely happens, I had been testifying, and the first thing that happened is it made it into legislation on the House side. Actually, a New Mexico congresswoman added that legislation to the House. It then made it into conference for the CHIPS and Science legislation between the House and Senate. I testified on the Senate side, and it didn't make it forward. It was supposed to go into commerce. And instead, however, in the way that it was originally envisioned, instead it shows up in CHIPS and Science Act. It legislates two sort of unprecedented things. It says that in addition to the science advisor to the president being required to have a quadrennial national technology strategy, which is unprecedented in our country, so once every 4 years we need a national technology strategy, and that's written by the science advisor to the president. In addition, the National Science Foundation Technology Innovation and Partnerships Directorate is supposed to, in consultation with the Interagency Working Group, identify and annually review and update a list of not more than 5 United States societal, national, and geostrategic challenges that may be addressed by technology, not more than 10 key focus areas. So what are our critical technology areas? And by the way, Congress takes it upon itself to list what those 5 are. I believe they include inequality and geopolitical challenges like China at that time in number 1. And in the 10 key focus areas, it's sort of like a list of a carburetor, a banana, and I don't know what else. But they're not really one technology per bullet, one dot. But they tried, right? And then it says this third one is the one that's really challenging. They said, and we want to evaluate the relationship between US societal, national, and geostrategic challenges and the key technology focus areas. And NSF TIP's going to do that for us. And I think you're all in the room because, as Eric already just said, well, wait, how the hell do we do that? Right? So that's the problem. So I had the opportunity to apply for a broad area announcement under NSF TIP. We had about 4 weeks to bring this together, which you could imagine if you're submitting to a broad area announcement in 4 weeks, that gives you about a week search time to find who you're going to engage. And we were able to bring together 13 universities across the country, Stanford, MIT, Carnegie Mellon. Jeanette's never going to forgive me that Columbia's not on this list, but the goal is basically to ask, how do you do number 3, right? How do we do that? And specifically, what NSF TIP was asking us to do was to put together a vision for national critical technology assessment, including what are the current capabilities across the country, what are the gaps in those capabilities, and what is the national investment and organizational form needed to realize that vision. So they wanted us to demonstrate how analytics could help quantify the value of different science and technology investments for the US's security, economic, and societal goals. And they also wanted to say, what's the advantage of, like, how could a whole, like, why shouldn't I just give out a bunch of grants as NSF, right? Or why shouldn't we just pay an FFRDC? Let's pay RAND or MITRE. Like, is there something where the whole's greater than the sum of the parts across our country? So that was the charge. And the way we set up this year was basically, if I walk away from this, online can't hear me. Is that correct? But I have a. Okay, so so we said, okay, let's do some demonstrations, and this was really what TIP wanted to see: is this even possible? What can we do today? So we did demonstrations, and then we run those demonstrations through a review process. This actually, the fact that we needed a review process, we figured that out about halfway through the way, thanks to our advisory board. And that review process was across academia, industry, and government. So we believe that in this case, we needed everyone at the table, not in the way that you would classically in academia just run it by academics. So we needed research integrity, but we also needed, for example, what would stakeholders think? Was this politically feasible? Was this politically infeasible? So we wanted to hear all of that. The second is then in building a vision for critical technology. Oh, sorry, I'm getting ahead of myself. In the exchange, what we did is we said, okay, how are we going to have government and industry and academia at the table throughout this process, right? Not just the academics go off and write their papers and 5 years later, like we all start talking about things. How are we going to do this throughout the process? And what we did is we set up a series of workshops thanks to the Sloan Foundation where we basically said, okay, throughout this process, and I was particularly worried about industry and agencies. I didn't want agencies to have wasn't developed here type of response. I didn't want DoD to say, well, we do industrial policy, or DOE to say, well, we've got our analytics group. So how do we have them at the table throughout this process with the academics? And the same for industry. How do we not have industry have us come out and then start fighting whatever our result would be? And I think I did not understand until we were largely done with the report that basically we had broken a rule in DC, which is that you're not supposed to have transparency throughout the process. And I say this actually a little bit not in full seriousness, because in many ways the concept was that to protect yourself from stakeholder interests, you should have a closed door activity, like even if you look back at the former OTA, and then you release the report and everyone responds. I guess I thought that we as academics are also bullheaded, that we were going to keep doing whatever we believed in because nobody was paying us in this case to do it, right? And I think that was true. And if anything, it was harder to move the academics to what agencies and industry cared about or thought were the issues than the other way around. And I think that was an important lesson because they loved knowing what was going on, even if they couldn't change. Right? If you think about the willingness to take advice, but not direction, right? They loved that. And then the last is on vision. We essentially ended up having over 100 inputs at the workshops on what a vision for critical technology assessment could be. We ran a survey, and then we did a structured report writing process that was much more similar to what you might think about in a National Academies report or something of that style in coming together with a vision for critical technology assessment. So after we ran all the demonstrations through a cross-organizational institutional review, so we had about 20, I can't remember which one's 23 and which one's 21, but we had roughly 21 to 23 area demonstration reviewers. And this is like chief scientist of Microsoft, chief scientist of Intel, various agencies relevant to each. We then, for the full vision, had another 21 to 23 reviewers who were leaders and thought leaders in science policy from academia, industry, but particularly in DC communication. And that was it. And then we released our report 2 weeks ago. Great. All right. The crazy part about this is that we were given a 1-year timeline. So literally, we applied for the money. 4 weeks later, the money showed up. And 12 months later, we were done. So basically, we had about 6 months to do demonstrations, another 3 months really to say how is the whole greater than the sum of the parts. We at the same time then had to finish off our vision. Here we're running these workshops throughout. We start our review process about here. So we're running the integrated demonstrations through review as of right here. That we're continuing to review with a full report, and then we're doing our press release. It was nuts. Okay, so in thinking about selecting demonstrations for this first year, and I should say also, I would not have made it through without my research group and the incredible team we put together. I'm not going to be talking about that today, but it was a nightmare. So anyways, so what we thought about is we said, okay, there was a big interest in and a big problem about a lack of situational awareness in terms of what are the capabilities in the United States versus other countries. This was expressed by the Department of Defense, Department of Intelligence, as well as a belief that LLM technologies could do better. And then in the area demonstrations, we tried to think about, okay, we're not saying these are the best technologies to have developed. We're not saying these are or to have looked at. We're not saying these are the most important questions to have looked at. We just wanted to choose some areas that were convincing enough that they were important. They might not be the only or the most important ones, but also some questions that were important. And so the questions that we asked emerged from the academics themselves. So in AI, and then we thought about what do these represent? What do these represent? And the goal really was, what can we say about the multidisciplinary capabilities that you might need to bring to the table to inform national technology strategy? So AI, semiconductors, biopharma, and energy were the general areas that we decided to do deep dives in. And then we do really deep dives. And the goal of the really deep dives was not to say, we're going to tell you the future of where national technology strategy should go, or we're going to tell you the future of where AI should go. No, it was just simply to say, if the government leveraged data and analytics to inform its national technology strategy, here's some examples of the types of things you might be able to do, right? Here's some examples, and maybe you could use these methods across these different areas. And so that was the goal. And in terms of cross-cutting methods, we then thought about applying them just in one area, just as one example of how they might work. We then did, our goal in part was also thinking about, can this like LLM global scanning of competitiveness, can that be matched up with the deep expertise we often had to have in here? And vice versa, can that deep expertise sort of inform the global competitiveness? So before this year, I would say that we only had 2 pairs in the entire group of 22 faculty who had ever co-authored together. And we had about 80% didn't know each other before. And so you can see here some of the cross-cutting connections that we did in trying to bring this together. And that was novel in of itself, and we'll talk about the challenges there. And in thinking about the multidisciplinary lenses we were able to bring to the table, in short, in each area, we ended up, and none of this was pre-thought, right? I tell you, we were like, all right, everybody, we got $4 million. What do we do? But in each of the areas, we basically, in global competitiveness, we said, okay, can we do one example of how LLMs and bringing together deep expertise, in this case in semiconductors, could lead to a whole greater than the sum of the parts. In AI, what they emerged as their concept for was, okay, actually we all have kind of similar data. We're looking at related problems. Can we somehow bring our data together in a way that the whole is greater than the sum of the parts across different institutions? In semis, what they end up doing is saying different disciplines are able to speak to different sub-problems of the broader problem of US semiconductor competitiveness. In biopharma, we basically set 2 academics head-to-head. This academic is an expert in generic drugs and supply chains. This other academic is an expert in public awareness and public participation. And so how can these different disciplines and different methods offer different perspectives on making the whole greater than the sum of the parts? What does the public think versus what do the experts think? And in the last case, in energy and critical materials, this is like my rock star group. They combined disciplines. Their inputs were their outputs. They have entirely new methods, entirely new results. They've got engineering and industrial organization economics working together. It was incredible. And so, yeah, they're cool. They're all cool. They're all cool. So in the global competitiveness demonstration, so here you have like James Evans, who's interested in predicting disruptiveness, and YY On at Indiana University, being combined with the whole team from semiconductors, really led by Hassan Khan, who's now in the Department of Commerce, continuing the work that we started this year. And so they were pairing with each other. We also were looking then in the domestic case, both about foundation funding, as well of critical technologies, also Josh Lerner in terms of VC funding of critical technologies, and also Cassidy Sujimoto in terms of equity issues in terms of the funding of technologies. But in this case, I want to focus on this one and how these two came together. So James had the capability with YY and also Dasheng Wang, and what's novel about what they're finding, and this is James's work, just to be very clear, is that he finds, according to a whole set of different measures, this was the first, that China has the highest share globally of scientific papers that cause existing research to pivot in new directions. That's what he calls prescient, that initiates new lines of research, that's disruptive, and that leads to emergence of new fields. And so when we first came out with these results, one of the big questions was, hey, Lee, one of the big questions was, what, is this real? Like, oh, wow, that's a lot of measures. So is this real? And so what we did in combining that then with the semiconductor area is YY An went in with, and also Lockheed Martin, the former director of DARPA, was like, oh, I don't know if this is real. I don't believe it. We had a lot of pushback at first. So we went in and we actually in a workshop, ran a workshop where we brought the experts in the table in one area and said, okay, we've just deep dove all the way in to something as specific as beyond CMOS and semiconductors. What's the future of computing in semiconductors? Because we have that expertise in our team. And it's real, right? So here's topological insulators. You ask the experts in that space. You're all going, I don't even know what a topological insulator is, right? Or 2D material channel FETs. And if you sit down with the experts in this space, and if you red hat this, this was a real, that people were like, yeah, that's right. So that's a real result. Okay. I'm not going to talk through, but I'm just going to briefly speak to, actually you have Lee Branstetter in the room, so he can speak to much better than me, the results from AI or from biopharma. I'm going to focus on the semis and on the energy storage ones because I think they're particularly instructive of the different ways different disciplines can speak to different things. But what I do want to say is just briefly the results from these areas. In the AI case, Dasheng really looks at opportunities for AI. So he's using more machine learning and LLM models to say, what are the opportunities for AI to accelerate scientific discovery? And so he uses prediction to say, where are fields underutilizing AI compared to their potential, and what would, if you had greater either collaborations or people who understood how to use AI in those scientific fields, what would be the opportunity? So you can actually see the difference between some fields and how much they're using AI versus other fields, whether that's economics or chemistry or material science. And then Eric and Lee really focus on the impact of AI on productivity and jobs, and using novel measures suggests that AI might be not only, and different data providing different perspectives on that, AI might actually be increasing productivity, might actually be increasing jobs both inside and outside AI. And then what does that mean given that the distribution of AI capabilities might not reflect that everyone would be benefiting from that, so maps of how that looks different. In the semiconductor demonstration, and I'm going to sit with this one, what they did is they decided that you could use, we just looked at, YY An's global situational awareness work to understand US competitiveness in the future of semiconductor technologies, that Neil Thompson could use his techniques on productivity to say what's the potential value to different markets of those next generation semiconductor devices, given that different devices affect different markets and have potential in different markets, so they wouldn't all have equal value. And that then with Granger Morgan, that he could use expert elicitation, which is a formal method if you look up in PNAS or otherwise. This is a survey and probabilistic method, not, it's not I just go and talk to experts, right? To identify technical bottlenecks and costs to commercializing those next generation semiconductor devices. And then finally, because of the current incentives for domestic facilities across the country to have foreign and direct investment come here, Christophe Camemmal uses novel methods, really combining techno-economic modeling and economics to ask what are workforce capabilities and what are the constraints to realizing this foreign direct investment in terms of workforce limitations, and how might that hold back our ability to compete. Okay, so I think for those who are not technologists, my background, I had a quantum physics in my qualifying exams. So for those who are not kind of normal, who are normal studiers of the field or industry of semiconductors, I think it's really important to understand that semiconductors are not one thing, right? So there are mature nodes, which you might find in your automobile or your medical devices. This is what was really where the automotive industry was screaming about the lack of semiconductors. And these mature nodes, I actually have a paper with in issues with Andrew around specifically this space, right? The US's challenge is vulnerable supply chains. And the type of solution is going to be really different in this space, and that's a different talk, than it is elsewhere. Then there's leading edge nodes. That's what we have today in computers or in cell phones. And there, again, our real challenge is vulnerable supply chains, but it's a different type of set of solutions that we need. Here, you have too much heterogeneity in design. So you have sort of short-term monopolies in the suppliers, or kind of monopoly power by suppliers because they're so specialized. In this case, in leading edge, your challenge is that basically all of production, 90+%, is in Taiwan at TSMC. And so you have a kind of a diversifying the supply chain challenge, which is why there's domestic facility incentives. But in the future of compute, you have yet another totally different challenge, right? So here, these basically to continue to advance AI, talk about technology interdependency in the next 5 years, really. Some would have argued shorter, but definitely 10. You need to find a new computing device, a new logic device. And so if we don't find a new logic device, you've already seen the decline of Moore's law and the implications, potentially, if you believe Neil Thompson's work, for productivity. So how do we find and lead as a country in this next generation of computing devices when there's fundamental physics challenges, yet no less development, scale-up, and commercialization challenges to that new technology, which is where you see, for example, the Department of Commerce's National Semiconductor Technology Center, which is trying to do that type of activity. So different problems and different technologies, we need to keep that in mind. In the case of bringing this foreign direct investment to the United States, there are announced facilities going in Columbus, Ohio, and in Sherman Denison, Texas. This is work by Christophe Camemmal, and I think it's just a beautiful, beautiful presentation of place-based challenges, right? So what you really can take away from this example that he does, now he can do it for different types of workers, but he has shop floor level data on different processes of what the skills are that are needed for semiconductor technology, so task-based skill data that is, he basically elicits ONET type responses from individual operators. He then takes ONET's skills across different regions, and specifically at metropolitan statistical areas, and says, what are the skills that are available in this region? And what you can see is that in Columbus, Ohio, if you are willing, so they need roughly 3,000 semiconductor processing technicians to run their facility for the FDI in Columbus, Ohio. And if you are willing to say, okay, there's not enough people with full 100% of those skills, right? And he does ask without cannibalizing the existing sectors that are there. And he has a second version where he looks at mobility and with cannibalizing. But so here, if you have 75% skill similarity, you still don't have enough people. If you're willing to relax that to 50% skill similarity, you can get you can fulfill the demand. Okay. In contrast, and now there's of course a whole bunch of questions. Can you take someone with 50% skill similarity and train them to become a semiconductor processing technician? And he actually does work looking at like, oh, look, a radiology technician looks awfully similar in the skill portfolio as a semiconductor processing technician, and they've just lost a bunch of jobs overseas, other work. But in Sherman Denison, Texas, where is another FDI location that is planned, here you can see that even if you relax this to 50% skill similarity, you don't have the 4,500 technicians that they believe they need. So now you're talking about about educating or training people who don't even have 50% skill similarity. That's a different lift, and you need a whole, like this idea that we're going to create a single national training program and everyone's going to get it. I don't know, maybe this needs a pretty different national plan and training program than this does, and that type of data analytics can inform those types of decisions. What else they did, so here you can see, and this was just very quick and cool, in my opinion. So they used LLM modeling to look at how much access US versus non-US researchers had to commercial fabs to commercialize their new prototypes and designs, because for beyond CMOS devices and even for current leading edge technologies, that's particularly important. It's been shown you have to, at some point, run your new design from universities in the fabs. And it turns out that over time, other countries, regardless of which those countries are, so if this is 2017 and this is 2022, they have systems set up for their academics to have access to those prototyping facilities in a way that we don't have set up equivalently in the United States. Academics complain about this, but you can see in the data based on publications that that's true. They're having to publish on older nodes in different facilities. Likewise, this is then, here you can see Neil Thompson doing productivity measurements, sort of more classic economics, of different devices given their market applications for the future of computing. And what we were able to say is that the current funding, or they were able to say, in the Chips and Science Act, as big as that is, that legislation for semiconductors, you would only, so it takes about $100 million to demonstrate one of these devices. Just prototyping it, given the capital expenses, takes about $1 billion to take that device and run it on a full enough facility that you can figure out how to bring it to commercialization. And this is talking to that range of experts through expert elicitation. You have enormous uncertainty. People thought it was going to be this device and then that device, and they don't know what the answer is. And so pretty much the issue is that we have in Chips and Science enough money right now to do the $1 billion on one of these devices. And given that you have no idea which of these devices is going to work, you're basically, from a portfolio perspective, not running enough experiments. And so we were able to see, in a very tractable way, instead of being like, more money for science, well, this is your situation, and you're running one experiment here, and you're probably, given the trillions of dollars in value for the economy, this is probably not the right balance overall. And meanwhile, other countries are closing the research gap in these beyond CMOS devices. Okay, I'm going to skip the recommendations because I think you've got them. In the biopharmaceutical section, they decided, in thinking about criticality, to focus on generic drugs. The reason they focused on generic drugs was the impact, the number of people impacted by shortages in generic drugs. And their question was, could innovation, like continuous manufacturing and investments therein, help overcome those supply chain shortages? And I think this is an awesome demonstration in the power of no, right? So the answer was no. The problem isn't that we don't have the technology. We don't want to be spending more money on this technology. The problem is actually that regulation, because in continuous manufacturing and the technologies that we need, regulation prevents, in generic drugs for safety, you changing the recipe, right? So if you have a novel technology and you want to bring it to market, and the regulation says you can't change the technology, you've got a problem. Meanwhile, I would say that also the novel technology improves quality, and the public has no awareness whatsoever that generic drugs have the extent of quality issues that they do. They're very aware of the access problem, but the public at the same time is fighting for lower costs, whereas you might imagine that in sort of the correct market situation, you would want the public to be aware of and willing to pay for higher costs because they might not be getting the drug that they think, or the government too, right? So that's that example. And I want to end on the energy and critical materials demonstration. So here, what the team was asking was, with the scale up, and I love this demonstration, because I think, as Eric was saying, like, how do we think about pathways? All of these are thinking about pathways. How do we think about what could we do? And I think so often we can get stuck up in needing to be able to predict the future. That's not what any of these are doing. They're trying to quantify the implications of the situation that we're in and bring in what the options are. So basically, they were saying with the scale up of electric vehicles, I have to look what my next slide is, what are we heading into in terms of supply chain shortages? And what they do in an incredibly powerful way that I think hasn't happened without bringing together engineers and economists was they're able to quantify why you care by using an industrial organization model. It's not just, oh, there might be supply chain shortages, and we'll talk about this in one moment. So what was very cool about this team is that they came in with a lot of models, right? They had a lot of capabilities already, a lot of data. So they had, on the Olivetti team at MIT, basically global market and supply chain data on critical materials across the country or world, critical minerals. Here they also had, Katie is someone who's in industrial organization and design and crosses those two, so they had existing models of the automotive sector in a way that they could model the industry organization, and they had existing models linking using techno-economic modeling specific, this is with Kumbamal as well as Cotterman and Katie as well, and myself, that we could link the difference between ICEV production and battery BEV production to labor outcomes. And if you'll note, this is like, I'm just going to do a little like, yay, engineering and economics. But basically, the UAW, there was this big thing going on about labor and so forth. And there were a number of papers that had said, well, there's fewer parts in electric vehicles, so therefore there must be fewer labor content. Well, if you're an engineer, and my first publication was in steel, and imperfections in steel, well, a vat of steel has no parts, and I can tell you that doesn't mean that it has no labor content. It has quite a lot of hours in terms of making that steel and quite a lot of expertise. And so we were able to quantify that actually a battery electric vehicle has more labor hours than a ICEV, and so that's part of that conversation is wrong, but all the labor hours are in the battery, in particular in cell production as well as pack production. And that means that who and where you make that battery is really what the argument's about. Anyways, but we're going to keep moving forward. So what they do is they take a whole bunch of scenarios, critical mineral supply chain stock scenarios. They're saying, okay, let's just put out some things that might happen. We're not predicting that these are going to happen. We're just running some scenarios. And so we're saying, okay, in lithium, let's say China restricts lithium exports. They also, by the way, ran what happens if China restricts graphite exports, just to, if you're looking at the news, they had that in there too. It wasn't part of this slide. But to 15% of reduction. What happens if there's a delay at a lithium mine that causes this much supply shortage? And they elicited from experts what might be possible scenarios that you could imagine, but they're not saying if these scenarios are true or not, right? They're just saying, here's some things that could happen. What does this look like? What happens if there's declining ore grades in nickel? What happens if there's human rights abuses and we limit our or reduce our draw on cobalt from China, from the Democratic Republic of Congo? What about due to climate change or otherwise? There's natural disasters in the DRC, and you can see graphites down here too. And what if actually they did put it on this slide. Yeah, what if PRC exports restricts graphite supply? So they ran that. What they do first is they say, okay, what are the impacts of that, right? So here, what they find is that there is a significant price increase of new vehicles, both conventional and electric. And this is matching these scenario modeling and techno-economic models to the industrial organization modeling, and that those are on the order of magnitude given uncertainties. Here you're just seeing three of these scenarios, thank you, to the semiconductor shortage. So both the 1 million households unable to purchase a new vehicle, the $24 billion of consumer surplus losses, and the lost wages and hours for battery cell and pack production workers, that this is big enough to something that we really cared about, right? So this was on the news. This looks like it could very much be on the news if it happens, right? So this to me is, wow, we care. And then what they say is, okay, if the world were a place where we could do any of these things, so let's say we could magically, through science or otherwise, or French, distribution of supply chain, changing the locations. They don't say this is how you have to do it. We could magically increase lithium supply by 100 kilotons, lithium equivalent. Basically, that largely reduces that vulnerability, right? That's what you would need to really get this out. And then they look at ways that you might be able to achieve that. So you could think about what do you want to invest in achieving that. Likewise, what if you could reduce 80% of, what if you could make 80% of battery electric vehicles not have cobalt in them? So lithium phosphate batteries exist today, right? So it's not that we couldn't use them instead. They have some lower performance attributes, but we're already using them in vehicles, but that would dramatically reduce our vulnerabilities, and as we'll talk about in a moment, it has some additional possible benefits. So all of these largely types of interventions largely help avoid these vehicle price increases and the consumer surplus losses, the loss of workers, the people, 1 million people not being able to afford a new vehicle. And then, so they say, okay, what are some immediate actions? You could diversify and sort of try to bring certain lithium mining capabilities up online in other places. And then also you could invest in cobalt-free battery performance to make that, as a government, to make that more, or just, you could just say, if you want to go crazy, you can say lithium, cobalt, you could get rid of all of these, right? But I think the question is, how do you reduce the supply chain? How do you incentivize if you reduce these supply chain vulnerabilities with innovations like cobalt-free battery? And then also on the supply side, technology investments in things like direct lithium extraction and other sort of alternative mineral and mining. The other thing that's a bit fun when you think about the objectives of government is that it turns out that, for example, cobalt-free batteries may also be robust to longer use and high-speed charging, which is low-income households don't plug in at their house. They have to do high-speed charging. And there's some early research that suggests that cobalt batteries, which is the predominant thing in industry today, actually could only go about a year with regular high-speed charging. And so you would also have equity benefits or distributional benefits of moving away from these cobalt batteries, if that's something you care about. Okay, so what have we learned from this year? The first is advanced analytics could be used to improve our global competitiveness awareness, right? What's our awareness of global competitiveness? Our awareness even of domestic capabilities. I didn't go through it, but they were actually in real time able to use data science to show that NSF was underfunding the leading scientists that were women in computing compared to what other funders were doing and compared to their citation counts and otherwise. We can also quantify supply chain vulnerabilities now, the scale of their impact, and also innovation and policy interventions that could reduce those vulnerabilities and impacts if you care about what those are. And then the last is there are methods that can be used to quantify technology commercialization pathways, whether that be policy investment and other interventions like gaps in the innovation infrastructure that might exist. So, for example, if you need that $1 billion and you don't have enough, we talked that through. Skill gaps, we talked through the skill gaps in semiconductors, but also public. So if the public isn't aware of the quality issues, then it's hard to get either government or the public to pay for them. Challenges, there's a lot. So we did the easy thing. We did situational awareness of global funding and publications. That's what's available. Obviously, the knowledge on the later stages of scientific and technological development, commercialization, production, are much less widely used. So if you look at our advanced manufacturing capabilities, most of that was working with private firms and getting private firm data. Timely data for critical supply chains, timely data for rapidly moving critical technologies such as AI. We had long discussions inside the team about these issues and the need. How do you, in AI, get access to the large firms that are currently maybe charging $20 million for access to that data? And how do you get the academic community access there too? In critical supply chains, you don't have the money to track everything. So how do you decide what to track? That's not an easy question. I mean, we took off small, low-hanging fruit here. That's a really hard question. And then that equity and including equity in each of these analyses requires very serious resources. So if you think about it, equity is not a single field of study. You don't tack it on after the fact. You need experts with complex analytic, technical, and phenomenological knowledge to address issues such as algorithmic bias, energy equity, health equity, and equity and discrimination in labor training. So to do that would require really bringing people with that deep expertise in each of the areas on board, not just some generic equity person on top. As well as leadership that even says that that is part of criticality, right? That's not going to happen on its own. I want to watch my time. So basically, we did talk a lot about how what the dimensions are of where you are on the S-curve in terms of discovery versus diffusion and adoption and commoditization, where you are in terms of US competitiveness, and where you are in the policymaking process really drives what the relevant methods are, what the relevant data is, and what the relevant questions are to ask. And that this is a bit of an art, whereas everyone who was brought to the table were scientists in what they do, putting this together in the multiple disciplines is truly an art. And that's a different type of thing. Obviously, we can use econometrics, possibly if the experiment was set up in advance, maybe even if the experiment wasn't, to look at policy impact only after the policy was done. If it's not even on the policy radar, there's a whole bigger lift that's required before you're able to get where you need to go. Two more things on cross-cutting lessons, and there's an entire 100 and I think someone recently from Federal News Network held up and he was like, so there's 154 pages here, and I was like, oh God, we've been academics again. But there was so much to say because of the openness of this field, and people's examples just speak. When we spoke to the House staffers, they were like, the examples help us know where you need to go. So I think a really big thing is to focus on I'm speaking to economists and social scientists, but focus first on the outcomes. I'm about to end on, I tend not to use the word industrial policy or industrial strategy because it's not clear to me that that's our goal. And I think that's unuseful in a certain sense. I did use when I wrote national technology strategy. So what is our strategic incentives? I think I joked to Eric, I think I'm doing industrial policy and industrial strategy. But I think that the goal is the outcomes, right? So the National Defense Authorization Act defines critical technologies as those essential for the U.S. to develop further the long-term national security and economic prosperity. Obviously, they forgot about things like health, which clearly could affect both of those, but or societal well-being more broadly, or inequality. So in each of the cases, we talked about starting with where we're trying to go. Are we trying to improve national security? Are we trying to improve economic well-being? And are we trying to improve societal well-being? And thinking about across those, what are the implications of these investments? So start at some level, it's a bit of a back and forth between the two, but thinking about the outcomes is where we want to go. The other is, this became a point of confusion that I hadn't seen coming. Technology assessment or industrial policy is not about prediction. It has nothing to do with prediction, I don't believe. It's even useful, and for a matter of fact, you can see here an example. Here's one example, and you can get 30 3,000 papers that all do the same thing. But so here was what experts forecasted in 2009 and 10 of likely solar electricity prices in 2030. Here's their cumulative distribution function. So this is what they thought the likely prices were going to be. That's in 2030, and they were in 2009. And you can see by 2019, the actual prices were already lower than any of their predictions across probability distributions. We as humans are not good at this. There is example upon example, paper upon paper that we don't do this well, that you can't take Moore's law and apply it to a different industry. You need deep contextual and phenomenological knowledge of what is actually driving that, which is, by the way, Dennard scaling, and following that equation, and then also following what is increasing more and more chips on the real estate of a wafer that drives down costs. So technology forecasts involve complex technological and social systems whose interactions and outcomes can be difficult to predict. And this is a gray box in the report, co-written by a founder of machine learning, Tom Mitchell, Granger Morgan, both of whom are members in the National Academies, who has studied expert elicitation and wrote the use and abuse of expert elicitation in the PNAS. And then a former editor of Technology, Forecasting, and Social Change. So they wrote this. For useful predictions to even be possible, you need stable patterns to exist. And part of what you're trying to do in national technology strategy is disrupt those patterns. And so forecasting of the exact times or precise technical developments should not be the primary focus of these types of efforts. What you need is you need to predict the general directions which people are saying are interesting. And I don't even like using the word predictions. We need to be aware of what we can be aware of general directions and how they could change, an analysis of what might be the gating factors in those technology advances, and what are the actionable policy interventions. That requires a lot less precision and can, with appropriate caution, can be of great use in driving and informing decision makers. So I think a bit of a question is then, how do you do this for the country and how do you do this in academia? I'm going to skip the next 3 slides and I'm going to do my last 3. I saw Eric look at his watch and I'm looking at my watch too, so I have time for questions. Andrew's just sitting. He's not reining me in yet. He should be. So I'm going to skip the lessons, organizational lessons, and I'm going to go to just the answer. So there's a whole. You can read the 154-page report, or skip to this section of it. So the CHIPS and Science Act calls for a new federal capacity to fortify the nation's leadership and ability to determine policies and investments that will ensure national security, global competitiveness, economic prosperity, and societal well-being. I think, oh, that's too bad. To operationalize this mandate, what we really were seeing is that the US is going to need to intentionally design a rapid critical technology assessment function. And that intentional designing, I believe, needs to leverage the incredible variety of disciplines and institutions. I mean, we also have FRDCs in addition to academia across the nation. This should not be done in-house in government, right, by another entity. They need to be able to synthesize, as I hope I've shown you today, and integrate distributed capabilities, distributed analytic power, and distributed technical expertise across the nation's rich variety of institutions and disciplines. And I believe this should be led by a single entity, right? Given the technological interdependencies, the fact that you don't necessarily, like I'm sure each organization would love to lead, whether that's the university or that's MITRE or that's, and anyone else would love to lead industrial policy for the country. But I think what we need to do is leverage all of us, right? And how do you leverage all of us in a way that brings together different disciplines? DARPA's done that historically pretty well in creating new fields. So it needs to be led by a single organizational unit charged to think across national missions and technology interdependencies, and that engages topic-specific program managers trained in the art of identifying. You can't solve everything, right? I think just going at the 50,000-foot level isn't very helpful for making decisions. So what are the most important problems? What are the matching of methods to problems so that you get the scientists who know how to do this at the table, the industrial organization economists and the techno-economic modelers and the engineers who don't yet know how to talk to each other. And that mobilizes and orchestrates that distributed national capability both within and outside government. So I do have an org chart of what I believe is needed, but what I want to focus, and I do think that you should have specific areas, but I want to focus on this last one in my last set of talks, set of comments, which is that I don't think we have a lot of people who can do this well today. And so when I focus on the building of human capital, I had, in conversations with others on this activity this year, we had a lot of questions about, are we just bringing together the capabilities across the country, or do we need a new field, right? And when you say a new field, and I think in large part for a long time, until a recent set of meetings I had as a part of a corporate visiting committee this past week, I thought, no, we're just orchestrating this across the country. We don't need a new field. We have all the fields. We just need to bring them together in new ways. But what I realized is that at Carnegie Mellon, we have a department that does that. We have psychologists and decision scientists and engineers and economists, and they all want to talk to each other. And we've been around for 40 years. And what I realized in being on the corporate visiting committee is maybe that's not normal. And so, sorry. So as much as I think the country needs a national technology strategy, and as much as I think the country needs a capability, and I would say an entity, an ARPA-like entity, to bring the country together and start to drive this type of field development, I do think that increasingly, I was sitting with a biochemist who has done, innumerable startups, is extraordinarily successful, who's trying to talk to an economist right now. Both are incredibly famous. And what I realized is that there was a whole layer in between that was missing so that they could talk the same language. And so that language, the biochemist was able to articulate that basically in being able to bridge biology and chemistry, he was multilingual in being able to do that. And what I realized is I think today we really need in each of the social science fields to be building these multilingual individuals who cross between technological expertise and that social science. So that's economics, or that's psychology and decision science, or that is sociology, or that is political science. I would say that capability has deeply atrophied today because the engineers, which I have one hat that I kind of feel like I associate with, you sit in a National Academies meeting and they think they know how to do policy. And on the other hand of things, the economists say, well, I don't think that it doesn't matter what widget it is, right? If we come back to my opening talks, and actually it does. The widget changes, and these technological interdependencies are deep, and so I do think we have a burden as a country to build these multilingual ducks, and on that I'm going to quote a student. A student at actually MIT's Technology Policy Program, which is a master's program, had stood up and said, because I have on my slide here when I was speaking at OSTP, that we needed these integrative research scientists, and the student said, the fastest animal, and I'm not going to get these examples correct, but the fastest animal on land is something like the cheetah, the fastest animal in air is something like the peregrine falcon, and the fastest animal in the water is something like the swordfish. I'm sure I've gotten it wrong. And then she said, and technology policy has engineers who then want to do policy. And are taught in the social sciences, political science classes, and economics classes. And she said, do you know what is the fastest in all three? We all stood there and said, no, we don't know. And she said, the duck. And she said, why does the world not understand the value of the duck? And that's the end of my talk.